Okay, so this presentation is going to be about porting CUDA code to SYCL. The main objectives are to learn how to port CUDA host code to SYCL and CUDA kernel code to SYCL. So two parts in this presentation. So let's first look at how we port CUDA memory management to SYCL. Obviously, before we can do anything with memory management in SYCL, we need to have a queue. CUDA malloc calls can be replaced by SYCL buffers. CUDA memcopy calls between device and host can be removed. The SYCL runtime will handle these memory transfers for us. CUDA memcopy calls between device and device will translate into a SYCL command group, which will just contain a copy command. CUDA free calls are also unnecessary in SYCL. We don't need to handle memory deallocation. The runtime does that for us. So this is a basic example showing how device memory can be implicitly allocated, synchronized, and destroyed in SYCL. This is in opposition to CUDA, where you have to explicitly allocate copy to device and copy back to host, and then free the memory. This makes the SYCL code much less verbose and more readable. So we start by creating a SYCL queue for your preferred device. Here we're replacing the CUDA malloc memcopy calls with just a single SYCL buffer. So that buffer is constructed with the host data, and the SYCL runtime will automatically handle copying and allocation and destruction of the data for us. Yeah, so as you may be aware, in the SYCL memory, in SYCL, the memory allocated for buffers is freed when the buffer leaves the scope. So that's why we don't need to call any free functions. In this example, we're copying data between buffers on the device. So in CUDA, this is done using memcopy with the device-to-device parameter. In SYCL, we have to submit a command group to a queue, get the accessors that from the buffers that we want to copy. Here we have access modes read for buffer A and access mode write for buffer B, since we're copying from buffer A to buffer B. So now let's look at how SYCL handles unified shared memory, or USM. This is USM provides an alternative pointer-based data management model to buffers. USM memory allocations return pointers which are consistent between the host application and the kernel function on a device. Pointer-based API makes porting from CUDA code easier. And this is especially true if you use a lot of CUDA malloc managed calls in your CUDA applications. So in order to use USM in SYCL, we do need to explicitly allocate and free the memory. CUDA CUDA malloc managed calls are replaced by SYCL malloc shared, and CUDA free calls are replaced by SYCL free. We have to make sure to explicitly wait for kernel completion before accessing the shared memory region by calling q.wait. You can also retrieve an event object from the queue submission and wait for that as well as an alternative. So this example compares the CUDA application on the left and the SYCL application on the right, both using USM memory. So here highlighted, we have the CUDA malloc managed allocation, and on the right, the SYCL way of doing this. Note that we have to pass the queue as a parameter to the malloc shared in the SYCL version. Yeah, once we submit the kernel using the USM memory, we have to wait for it to finish before we can read the results, and this is true for both CUDA and SYCL. And finally, the CUDA free call is replaced by SYCL free, which also requires the same queue parameter. So CUDA kernel's execution range is defined by passing the number of blocks per grid and threads per block. So you can see the invocation here. In SYCL, using SYCL's ND range to define the execution range, we have to specify the global range and the local range. So instead of defining the number of blocks, we have to specify the global range. And the SYCL global range must be divisible by the local range. So in SYCL, local range is the threads per block in CUDA. The SYCL global range is the CUDA blocks per grid times threads per block. So converting the CUDA kernel invocation to SYCL, we need to calculate the global range. So this is an example of launching a 1D kernel in CUDA and an equivalent example in SYCL. So you can see on the left we have the standard CUDA way to do this. We define threads per block and then calculate blocks per grid based on the size of our data there. On the SYCL side, we define the local range. This is a one-dimensional range. This is the template parameter one. And you can see here the calculation to get the global range. Finally, we construct an ND range object from our global range and local range. And this is finally passed to the parallel for interface. This is passed to the parallel for interface. And then here we have the kernel implementation, which takes the ND item object or type. So thread indexing in kernels is a little bit less tedious in SYCL than CUDA. CUDA kernels expose two variables providing the grid and block dimensions and two variables providing block and local thread indices. So this means that if we want to find the unique thread indices within the global execution range, we have to perform some calculations. And you can see on the left this calculation to find the global linear ID for a kernel invocation. And this is a 3D invocation. But SYCL provides functions to easily retrieve these indices with just one function call.